adherence to the presentation. If at any time you are experiencing difficulties in hearing the webinar, please first ensure you have a stable internet connection. If you are unable to hear, please type in the chat box or click raise your hand button and our team will assist you. If you have any questions about the presented materials, please lodge your questions into the Q&A box. All responses will be given by the presenter after the presentation. First of all, I would like to introduce to you about POPSIG. POPSIG is a not-for-profit special interest group under the umbrella of the UK-based Institution of Chemical Engineers, ICHE. We focus on the chemical engineering practices in palm oil industry. We provide a forum for exchange of ideas, the sharing of experiences, and encouraging innovation in the palm oil processing industry. But our membership is not restricted to the chemical engineers. Our major activities are webinar, forum, university roadshow, as well as delivering newsletters, awards, and bursaries to the students. If you miss some of our live events, you can always view the summary on our newsletter webpage. The upcoming event, Palm International Nutra Cosmeceutical Conference, PINC 2023, will be held on Tuesday, 22nd August 2023. The theme of PINC 2023 is Unlocking the Potential of Palm Bioactives in Nutra Cosmeceutical. It will be hosted by MPOC and will be held in Lem Meridian, Putrajaya, Malaysia. The registration fee will be collected by MPOC is 300 Malaysian ringgit per person, and we will announce more events in the coming weeks. All POPSIG hosted webinars are free of charge and open to all. Lastly, we would like to thank you to our sponsors and partners in 2023, Desmet Malaysia, KOK Oleomas, Malaysian Palm Oil Council, MPOC, Malaysian Oil Chemical Manufacturers Group, MLMG, and Sime Darby Oils for their support to POPSIG activities in 2023. Before we move on to the presentation, I would like to introduce to you the speaker, Mr. Nick Mohammed Farid Yasin. Mr. Farid is the head of processing and engineering at the Sime Darby Plantation Research Sedang Berhad. He obtained Masters of Engineering Technology and is responsible to lead the modernization efforts in palm oil mills, while upholding sustainability as a paramount focus. His achievements include the successful filing of 4 patents centered around oil recovery enhancement and wastewater management. Now I would like to pass the floor to Mr. Farid for his presentation. Mr. Farid, back to you.
Okay, Assalamualaikum and very good evening. Thanks, Melvin, for the kind introduction. So today I would like to share in terms of the Sime Darby Plantation research experience towards the zero liquid discharge for palm oil mill. So in terms of the research-wise, we are looking at how we can enable the treatment for palm oil mill effluent from the current stringent requirement of BOD 20 milligram per liter. And then from there, we want to improve further until to the most stringent requirement, which is the zero liquid discharge, meaning to say 100% of it being recycled back to the mills for the mill process and also other usage and utilization. So looking at the current production from palm oil mill, taking from the estate itself, FFB, and then after that we are producing the crude palm oil, our main product. We are also producing a lot of byproducts. We do not call this as waste because there are a lot of values that we can derive from these byproducts. The one that I would like to highlight here is the empty fruit bunch, whereby one of the common usage that most of the millers are doing now is on the composting plant, whereby we convert EFB to compost and then we put it in back into our plantation as a soil conditioner as well as fertilizer supplement. But moving beyond that, EFB and also pomade itself, our effluent itself, we can derive further converts towards other valuable chemicals and materials, for example, bioethanol, bioplastic, and biohydrogen. We also have other byproducts, shell and decanter cake, whereby we can, for example, decanter we can convert to animal feeds, and then shell we can convert to other carbon-based products, for example, carbon nanotubes, and then the latest one is graphene. And with fiber, as of now, we are using it as our fuel. So with the byproducts, we can embrace the circular economy, whereby all the byproducts can be reused back or converted to useful materials. So, and then a part of it is the palm oil meal effluent. So looking at current process, there are two ends for the palm oil meal effluent. After being treated, so it's either we reuse back as a land application or land irrigation, meaning to say we return back to our estate for water usage, or we treat good enough to the extent that we are allowed to discharge the water course to the river. So that's the current state for the palm oil meal effluent. So before we looking at the problem that we have, let's look at what we have first. What we have first in the place, whereby with palm oil meal effluent, we have enough so-called nutrient inside there, the COD inside there, whereby we can generate electricity using an aerobic process. So that's why we are using biogas plant in our mills. With that, we can generate electricity, produce renewable energy, and then either we use it in our mills through co-firing or convert to electricity, or otherwise we sell it back to the grid. So that way we can further improve our sustainability by self-sustain in terms of energy. And then we, in terms of the another technology that we have, currently we already have, is the solid removal and the watering system. This is basically to automate in terms of the system maintenance. As I mentioned before, we have the solid removed from the pond for animal feed. This one can be used for fertilizer supplement. And then we have another treatment until we are reaching to the water bodies and then comply with the BOD 20 compliance. So all of this we already have, and then we already comply to the most stringent requirement by MPO, by DOE, Department of Environmental of Malaysia. So with all the system in place, why we need to see the gap and then the problem we are facing now, so that we can further improve and then a step forward towards approaching our target, which is the zero liquid discharge. The first problem that we face, basically in terms of the volume of POME discharge itself. So we're looking at every 1 ton of CPO produced, we are producing POME, our effluent, at the rate of 3.5 ton. So it's a lot of effluent being produced. And then due to the nature of the treatment that we are using currently, we have the ponding system, we have the biogas plant, all of that. The area requirement also is very big. So we are looking at, sometimes you can look at the photo here. This is the mill itself, and then this is the area requirement for the system to treat POME until we can discharge to the water bodies, to the river. So let's imagine if we manage to develop something and then we retrieve all the areas and then we can use it for something else, power generation, solar panel, or we can do replanting on the reclaimed area. I think this is where the major issues I think most of the companies face. We already comply with the stringent requirement, POD 20 milligram per liter. However, the end product still reddish color as per shown over here. Based on analysis and based on the data that we had, it will not bring issues or any harm to the animal fish inside the water bodies. But because of the color itself, the public perception still saying that we are discharging so-called dirty water into the water bodies. In fact, we already treat it good enough for us to discharge to the water bodies. And then last but not least, it will be on the water footprint. As of now, in terms of the the focus area that we are looking at is on the carbon footprint. But once we manage to sort out on our carbon footprint, aligning with the nation's requirement of the carbon net zero by 2050, the next will be on water footprint. We want to reduce as much as possible so that we can make use of the remaining clear water for other purposes. Okay, so when we looking at this, we need to look at the gap, the technology that need to be developed for us to achieve the target. For us to achieve zero liquid discharge, meaning to say 100% of the wastewater, the palm oil mill effluent, need to be reused back or recycled back for the process or converted for any other usage. So there are two stages whereby we want to proceed. The first one basically to reuse as processed water, meaning to say we treat as much as possible that we can reuse back as the processed water, meaning we can use the water for part of the process to purify the crude palm oil during the production. So one of the requirements here before we can reuse back the water, basically on the color itself. Even though the BOD is still okay, as I mentioned before, we want to remove the color. But even if we manage to achieve to that quality and then reuse back for processed water, the amount that we use in the palm oil mill will not be able to cater the amount of pomade being produced. Roughly, we are talking about only 50% of the treated pomade able to reuse back for processed water. And then the rest of it, we still need to discharge. So for us to be 100% recyclable, so we need to look at another use case whereby to be reused back as a boiler feed water for boiler treatment to produce steam for energy as well as for process usage. So these are the two stages that we have identified if we want to proceed with achieve the target of zero liquid discharge. Okay, there's come the idea on how we want to go towards the colorless discharge. So looking at the available technology in the market, and then we observe there's a new technology being used for the leachate treatment plant. The name is electro-oxidation, whereby using the electricity instead of the microbe to degrade the organic contaminant inside the wastewater. So we work out with a local technology provider to bring this technology to palm oil mill. So the time-lapse video here shown the how simplified in terms of the lab scale, how the electro-oxidation can remove the color of the palm oil mill, the pomade itself. So what happened is electro-oxidation is not really new technology. It's being researched and then studied in the journal for quite a lot of it for quite some time. But to bring to the commercial, there's not much success yet, mostly due to the capital expenditure as well as the OPEX. But when we develop together with the local technology provider, instead we go with only 2D electro-oxidation chamber, whereby we only have anode and cathode. We go towards the 3D electro-oxidation, whereby we introduce bipolar particle in between of the anode and cathode. So with this, we managed to increase the surface area as well as improve the reaction rate. That's why when we, after the study, we managed to bring down the capex as well as the opex to the acceptable level. Then we can proceed further with the commercialization trial. So 3D versus 2D, that's where the first innovation comes when we want to scale up. And then to brief everyone in terms of what happened inside the beaker. It looks very, very simple, whereby after a certain time, all the contaminant seems to, the froth happen, and then the color being degraded. So basically, there are two types of reaction here. The first one is the direct oxidation, which is at the plate itself. So there are two types. The R is the so-called the simplified chemical reaction. The R is the contaminant. whereby at the surface of the plate, it's being converted to the another material. Some of it we precipitate out, and then we can remove it via filtration. And the other one is further oxidized until become a carbon dioxide, as mentioned here, the incineration process. So the contaminant either removed after being degraded up to carbon dioxide and precipitate out as a solid from the from solid, then we can precipitate out and then filter out in the next process. The other one that happen is indirect oxidation. If you notice here, the reaction still occur at the beaker wall of beaker in between of the plate as well, as mentioned as inside the diagram here as well. So it's a indirect oxidation whereby we have several ions inside there that already exist inside the water. Together with the, when we introduce the electrolyte, we have the chlorine, we have the sulfide. So all of it will be converted into a strong oxidizing reagent. We have chlorine, we have hypochlorous acid, we have H2O2 hydroxy radical. So this is part of the equation and the anodic reaction. So with all of this, direct oxidation as well as indirect oxidation, from the oxidizing reagent, we managed to remove the contaminant good enough that we produce not only standard A, BOD 20 milligram per liter, but also colorless effluent. Before this, the only other technologies that managed to remove color is either membrane or ion exchange. However, at the expense of cost lah. So this is another alternative to remove color from palm oil meal effluent. So looking at the theory just now, how we want to implement this at our current setup. So we, as mentioned before, we have biogas plant, we have solid removal and dewatering system. We also have previously extended aeration as well as membrane filtration. So electro-oxidation will replace the aeration process. So biogas plant, solid removal and dewatering system will still be there because we can extract the valuable energy. We can produce solid from the removal whereby we have nutrient content inside there. So we're going to replace the extended aeration with electro-oxidation. So I will brief in terms of roughly what's the technology all about. Since we are using the electrochemistry route, so conductivity is very important. So that's why electrolyte is to be introduced inside the mixing tank. Type of electrolyte will depends on the pH and what kind of indirect oxidation that we want. If we want to go towards chlorine based reaction, then we can use sodium chloride, hydrochloric acid. Or if we want to go towards the sulfate based, oxygen based, we can use sodium sulfate or sulfuric acid. So electrolyte will be based on case to case basis. And then we have the electro-oxidation chamber. So design wise, we need to decide which is the best plate arrangement, what kind of electrolyte being used, the plate material itself, what kind of material we are using. All of that need to be considered and then design into the process. And after the treatment wise, the pH by right will increase to the 7. So regardless of what is the initial pH, certain journal they go towards the alkaline reaction, it will reach up to 7. If we go towards the acidic as well, it will increase to 7. However, we still put it the pH adjuster so that we can have a solid 7 to 8 range to prepare for the next stage for the boiler feed water treatment. So we have the pH adjuster. And then after that, just now I mentioned about the precipitation. So we have the sand filter and activated carbon filter. So to further polish the effluent. With that, we managed to get, well, here is the feed material. after the biogas plant, after the solid removal and dewatering, we managed to get the treated water colorless. So with this, we can win the battle of perception because we already produce good enough water to discharge, and in fact to be reused back for processed water, as well as colorless, as good as mineral water colorless. And then we achieve the color, in terms of quality wise, we achieve these 5 pillars: the BOD, COD, color, and TSS. Over here, we still not yet achieve zero liquid discharge, but we managed to achieve minimal discharge. So previously, this can be used for processed water, but not 100%. So some of the balance of the treated effluent still need to be discharged to the water course. That's why we use the term minimal discharge. So this is the video. The feed from the process, we already adjust the pH, adding up the electrolyte. Then we have AC-DC transformer. We're using DC current instead of AC. And then this is a simple electro-oxidation chamber that we have, a simple buffer tank. And then we have a pump. We have a microfilter, sand filter, and activated carbon filter to polish, remove any precipitation from the system itself. Okay, and then this is the water that coming up from the treatment that we have. So it's very simple, and then easy for us to automate, and then easy for the so-called operator to run the system. So with all the figures that we have, and then the testing that we had done, so what we are doing now, where we are now on the electro-oxidation to achieve that minimal liquid discharge. So basically, we are putting up a commercial plant with capacity of about 15 ton per hour, 15 meter cube per hour at one of our mills in Johor. So the system is almost completed. We are finalizing the installation, and then within a short period of time, we can start to do the commissioning and then run the process to verify our data from our pilot plant. So this will be the, I will say, still trial, commercial trial at one of our mills. The process flow still maintain the same. We have the filtration, we have the electrolyte addition, and also the electro-oxidation. If you can see here, this is where the chambers align. We have 12 chambers over here to cater for that 15 ton per hour capacity. So what we want to highlight here, when we install a commercial trial, we try as best as possible to make it future-proof in terms of the system. This is not just a trial to us. We want this to be some to showcase our innovation. So inside this electro-oxidation system, we already putting up inline automatic analyzer for COD, AN, TSS, and pH. So with that, the system, the analyzer will continuously monitor the water we produce. If there is no, for some reason we do not comply with the targeted quality, then it will automatically recycle back to the in front. So we're not going to discharge any non-compliance wastewater. So that's the plan that the sensor that we already put in place. We also try as much as possible to fully automate the system. We are looking forward to a wastewater treatment plant whereby we have a minimal manpower, some sort of refinery vibes. We have a room, they can stay in the room and then control from that room itself, and then everything can be controlled using the tablet. So at any time they can do the correction and then monitor the quality. So all the system, the dosage determination, on-off pumps, everything is based on sensors and also analyzer. So that's what we envision, and that's what we are putting inside the commercial system at our mills. And then last but not least, we focus on the minimal discharge. And then water footprint reduction, we are talking about roughly about 20 to 25% water footprint reduction. And the highlight here is on the colorless. We managed to produce colorless discharge. So with that, we've done with the minimal liquid discharge. So the next stage will be on the zero liquid discharge. So from this, I put up another characteristic over here, which is the total dissolved solid, about 8,000 milligram per liter. The reason why I put up total dissolved solid here, because one of the criteria for us to be able to recycle back the boiler used as a boiler feed water is the total dissolved solid. So it's a very big jump, TDS from 8,000 milligram per liter down to 100 milligram per liter. This 8,000 is the worst case scenario. Normally we getting about 4,000, 3,000 milligram per liter, but we make sure the system, whatever system that we want to put in place for our boiler feed water must cater for worst case scenario. A boiler is not cheap, so we need to make sure we do all our best to prepare the pre-treatment for that feed water. Then we scour the screen, the technology, look what is available for us to focus on reduction of the TDS. We have a screen and then select 4 of them. Number 1 will be on this is status quo, the best technology, status quo reverse osmosis system. And then we have another system that is ongoing trend now, electrodialysis reversal. Some of the desalination plant has started to use this technology itself. We also have again electro-oxidation, whereby we can see how we can further use the same technology to further reduce the TDS. The last one will be on the ion exchange, basically a dimming plant. So a bit detailed, reverse osmosis, we are using pressure to push the water from the more concentrated to less concentrated stream. With this, we're producing water with very less TDS, because TDS will stick to the retentive area, the reject water. And then we have ion exchange. We are using the charges from the resin to absorb the TDS that we do not want, the opposite charge contaminant. From there, the water coming out will be very pure. We have again electro-oxidation. This one we make use of the redox potential, how we can precipitate out the element inside there and then filter out, so we can further reduce the TDS. And then the last one will be on electrodialysis reversal. So for this one is upgraded version, I would say, for electro-oxidation, whereby we have a cationic and ionic membrane inside in between of the plate. So with that, we can separate the movement of the ion, restrict the movement of the ion, and then produce the pure water. So all this we evaluate using the discharge from the pilot plant instead of commercial plant, because commercial plant still under construction. And then after that, we found out for reverse osmosis, we managed to obtain roughly about 50% of water recovery using 2-stage RO, meaning to say the permeate need to go through 2 times of RO to get from 8,000 to below 100. We also, because when we do the reverse osmosis, the reject will be concentrated with TDS. So what happens if we use that as reject water? Because if we do not utilize the reject, we create another problem, because we need to treat that before we discharge. We test that, and then we test until we get to the both the quality for the crude palm oil as well as the refined palm oil. So there's no issue to use it. So meaning to say, after you have removed all contaminant using electro-oxidation, the reject one still we have no problem in terms of quality. The next one will be ion exchange. In terms of the regeneration cost still acceptable. We managed to get the so-called the total dissolved solid, our target below 100, in fact 0. However, when we start to do the regeneration, the amount of water required for rinsing is very high. And then the rinsing water, then water that we use during to regenerate back, we produce secondary wastewater, whereby we need to further treat that one. So that's the issue with the ion exchange. On the electro-oxidation, is very fluctuating. We achieve average of 60% TDS reduction. During that time, the average about 2,400 ppm down to 920 ppm. The problem is we based on what's inside the wastewater for us to set the electro-oxidation when we want to remove the TDS, because their millivolt, their volt will be different. So with our current process, taking the water from the river itself, so the content, the dissolved solid inside there will be varies. So it's very difficult for us to operate the EO letter, and then we need to have several modules of it. So that's why we, apart from not achieving the target, but it will be very difficult to operate the process. The last one, the new one, will be on the electrodialysis reversal. When we first tested on this one, we know the limitation will be on the capex for this system. Since it's a new technology, the cost is very high. When we do the literature, it's possible for us to produce instead of just concentrate, we can produce 3 streams instead of 2 streams. One is pure water, and then one acid, and then the other one is alkali. However, during the testing, we managed to get the TDS requirement. However, we do not manage to produce the product of acid and alkaline, therefore making it difficult for us to scale up later to cover for the additional cost of capex, the high capex. So with that, with all the figures that we have, we believe that as of now, in terms of combination for us to achieve the zero liquid discharge, it will be combination of electro-oxidation and reverse osmosis. EO for us to pre-treat, I will say EO as a pre-treatment now. When we are talking about zero liquid discharge, EO will be the pre-treatment for reverse osmosis. There might be opinion whereby we can just using the current process until extended aeration, we produce brownish or reddish effluent. Immediately we can put up reverse osmosis. The answer will be yes, we can get the quality that we want, but it will not be sustainable because of the loading. The color, the organic loading that we have from POME under normal conventional will expedite the replacement of the RO module. So that's where the issue, if we want to directly implement RO, and then that's where EO comes in as enabler for that. With EO, we can reduce the contaminant not only on the organic one, but we also can able to remove the color of the wastewater treatment. So with that, what's next? What we want to do? How we want to validate? We have the data, but we want to further validate the data that we have by side streaming the commercial EO plan. So once the commercial EO plan completed, we already installed the pilot plant RO, the one that we tested before, but we put it so that we can make it more easier to operate, everything being dosed in line so that it becomes sustainable when we want to operate for a longer period of time of this pilot plan. So it's on the validation afterward. So once we have validated, then we can review back our target with complete zero liquid discharge, everything being recycled back, whether we can achieve water footprint reduction 50% by recycling that 100% treated POME. Why 50%, not 100% water footprint reduction? Because as of now, we are using the water for boiler. The steam is not recoverable. So if we just recycle the pomade, 50% is the best. If we want to go further reduction of water footprint, then it will be on steam recovery after this. So with that, I believe that's the end of my sharing today. Hopefully, once everything done, we have completed the evaluation at site, then we can share further the developed technology so that everyone can move towards the reduction of the water footprint. I say with that, thank you very much.
All right. Thank you for the very insightful presentation, Mr. Nick Farid. That was not only about palm oil processing, but a great enlightenment on the electrochemistry knowledge of the audience. So I'm Hema, I'll be the moderator for this Q&A session. Important question, is the water safe to drink and have you tried it?
By right, if it's already comply with the so-called the boiler feed water, because it's more stringent than our normal drinking water, it's safe to drink, but I won't drink it.
Okay, so
let's give it for our boiler to drink.
Okay, so the next important question, how much is it, the cost to treat it, the whole thing?
Okay, the whole thing, the one that we have so-called solid figure based on our pilot plan will be the EO. We are looking about 3 ringgit to 4 ringgit 50 cents per meter cube of pomade, the cost to treat it. In terms of RO, based on our pilot plan data, we did discuss with several RO suppliers. They mentioned about roughly about 2 ringgit to 2 ringgit 50 cents. So all of these figures based on our pilot plan. So that's why we need to run commercial one EO to verify on that figures lah. As of now, if you're talking about all-in figure from treatment of pomade until the zero liquid discharge, we are talking about roughly about 6 ringgit to 6 ringgit 50 cents per meter cube.
Okay, yeah. So I'm sure implementing like sustainable measures, right? It's going to be cost intensive. It requires a big investment cost. So how do you manage your stakeholders, like the operating units, and how do you create awareness among this supply chain stakeholders?
Okay, because if we're looking at the cost per se, yes, it looks in terms of is definitely higher than what we have now, but we're looking at the intangible benefit that we can produce. As I mentioned before about the land itself, we are looking at the reclamation of the land. So with that, we have another area suitable for another mill to be developed. Many opportunities over there, solar panels, CO2 sequestration, and other things that we can use that area for. So that's number one. Number two, the cost after certain tax, sustainable tax being implemented, we are looking at, for example, Singapore, right? Singapore, they already have a carbon tax implemented. So moving forward, we're not sure whether there'll be water tax or anything. So with that intervention from the government, so the feasibility of it will start to change lah. So as of now, it looks expensive, but with intervention from the government and also by research itself, just to give a sneak peek, the cost of capex might be further reduced if we do some more research on the materials. So what we have now more in terms of direct, I can say direct technology transfer from the leachate plant. So whatever they have, we switch it to our process. So that's the cost that we need to bear. But we are also looking at optimizing on our own, so that after that the cost will be further reduced, capex and also opex wise. So yeah, I think it's very interesting to looking forward on this development.
Okay, all right. Moving on to the next question. What standard can we refer to the output of this system, the water discharged or the recycled water?
Okay. In terms of the depends on the first requirement I mentioned before is standard A. When I mentioned standard A, it basically is the IETS Standard A, Industrial Effluent Treatment System, Standard A. So under there, there's a couple of parameters. But for zero liquid discharge, for example, for Sime Darby, we are looking at the boiler feed water. So every mills have their own standard for their boiler feed water. Certain mills, they are looking at 200 TDS, but for Sime Darby, we are putting at 100 ppm TDS. We have silica, we have hardness inside there. For example, hardness must be below 5. So all that parameters is, I would say, depends on the process control in the mill. But as general rule of thumb, TDS below 100 and also hardness below 5. These are the two important characters.
So there's another question regard to the specification, right? Referring to slide number 6, what is the oil and grease content in the treated effluent?
Okay, basically we will get MD, not detected. In fact, oil and grease is, I would say, the enemies for electro-oxidation. That's why we need to remove it from the earlier stage. If you notice in my last slide, we have that so-called some sort of filter press there. So that will be our guardians lah for the process. We remove oil and grease in the pre-treatment so that we have not detected from the beginning. And then when it goes to the electro-oxidation chamber, then everything's just for the organic contaminant removal only.
Okay. This is regarding the online monitoring. So the auto-analysis system, is it using built-in calibration curve online sensor? And how close is the reading to the manual analysis using chemical, for example, COD or the AN or the TDS?
Okay, so for this one, since the plant is not run yet, when we discuss with our collaborator, basically they already have the calibration curve inside the online sensor. We still need to do the calibration, meaning to say when we run the plant, we look at the reading from the analyzer. We use the normal analysis, then we're going to recalibrate back the results. So some calibration need to be done, even though it's already built in.
Okay, yeah. So what specification of the membrane you use for reverse osmosis? Is it a just normal or a standard spec?
Okay, for this one, it's just a normal standard spec. We already have the pilot plant, so we just request our supplier just to provide a normal desalination membrane. We do not want to use a customized one, which will increase the cost later on. Anything that the normal one, then we can get it over the shelf.
Okay. Do you check the chloride and silica content in the treated effluent? How low are they?
Okay, I do check the chloride content after the electro-oxidation. So we managed to get some of it below, not detected, some of it, because after that we using the activated carbon. On the silica one, unfortunately, we do not check in terms of treated water. But when we discuss with the suppliers of that RO membrane, reverse osmosis, and then some of the figures from our other plants that we are using RO for the raw water treatment, the silica should be below the target limit. But I not remember the requirement. But
Okay.
silica and hardness shouldn't be any issue lah. TDS will be the main issue.
All right. How do you maintain the conductivity in the POME during the EO process?
Okay, inside
How do you
the
maintain the consistent conductivity?
commercial plant, we have the conductivity meter. So we already set the set point, and then based on that set point, the pump will dose on their own. But looking at when we take the sample during the pilot plant trial, everything, the range is almost consistent. So we do not see we have problem to maintain the conductivity. The range is almost consistent. But let's say something happened, we have sensors to detect and then to change the dosing accordingly.
This water treatment, is it after anaerobic digestion?
Yep, after anaerobic digestion, after the biogas plant, then we remove the solid using the standard dewatering system.
Okay. Aside from DOE compliance and positive public impression, are there any financial gain to using EO for colorless liquid discharge?
Direct financial gain, I would say no, because if you're looking at the cost to operate EO itself, compared to conventional ponding system, obviously it will be more expensive. But as I mentioned before, the intangible, we're going to be able to reclaim back the land, the aerobic ponds, the facultative ponds, and then if you are using ponds, we're going to create more ponds. So your area, your land will increase for the wastewater treatment. So all of that, if we put it intangible, and then we're looking at the use case for the land, then it will bring the values. So it's more towards that approach instead of we looking at the cost itself.
Okay. So I think this is also regarding the oil and grease content, right? So is there any concern about oil carry over to the boiler if the recycled water is used as boiler water?
Yeah, there is a concern. Of course, there is a concern, but before it can reach to the boiler, our analyzer COD will definitely catch up. We're going to return back the water to the initial stage for further processing. We have that three-way valve over there to recycle back the water. There are two. We have another safeguard system. If the filter press is not doesn't manage to sufficiently reduce, there's another one that we prepared inside there. So we have two-tier treatment system for oil and grease.
Okay, all right. Looks like someone is very excited about this. So which mill is the EO pilot plant being tested? Is it open for us to visit? So is it open to visit?
Definitely open for visit after it's being completed. So
Okay.
we're not going to keep the technology to ourselves. We're going to promote it to everyone else. Yeah.
Okay. There's another question on the electrolyte. Have to be careful in selecting the electrolyte type. Avoid chloride type to avoid 3 MCPD in the CPO if the treated water is recycled to the process. I think it's more of a comment and concern from the audience.
Yeah, agree on that. So we need to make sure. That's why one of the system that we have is the activated carbon. So if we want to use chloride, we will going to make sure that the amount is not that high, and then whatever balance will be absorbed by that activated carbon. Thanks for the advice. Definitely we put it.
All right. So have you considered increasing the salinity of the POMI for better EO conductivity?
Yeah, yes, that's the use of the electrolyte.
Okay.
That's how we increase the salinity.
Okay. Does the system affect the downstream anaerobic or aerobic processing?
Basically, the system will replace the downstream from anaerobic and aerobic. So no more facultative, no more aerobic and polishing plant.
Okay. So during your beaker demonstration, right, we could see some scum formation in the beaker. So in larger scale operation, how do you handle the scum formation?
Okay. When after that process, we're going to have another dissolved air flotation system. So which will concentrate that so-called the froth, and then it will skim out from the process. Only the water will go to the next process. So yes, we need to have another system to cater for that. The froth itself. It's actually a good indicator. The color itself will show whether your system works or not.
Okay, all right. So does your system include any CIP for cleaning?
We have the system because in the worst case scenario, if the pH, the condition of the pomade is not to as per design, you can have a scaling onto your plates. So with that, you need to do some cleaning up based on our experience, because we are running at the lower pH side, so we don't have that issue. But for the commercial plant, we have that facility to do the CIP if required.
Okay. So in your personal experience, is it like, does it require heavy maintenance? What are the technical challenges if it were to be deployed in larger scale?
I would say the technical challenges, maintenance wise, there's not much moving parts over there. It's only pumps. Then I will not see in terms of maintenance, but I would say in terms of how the wastewater itself, in terms of the fluctuation of the so-called the feed to the system, even though we already have all the sensors being placed, but they have their own limitation. So we need to make sure our process itself, the mill itself, stable, so that the effluent being produced stable. Then we can properly treat the system at the cost-effective manner. We want the stable feed going to the system. Yeah.
All right. Okay. I think with that, right? We have come to the last question as well. Okay, there's one more just came in. So I think SDP has methane capture facility to treat methane release from POME. With your zero discharge, how can this interplay? Will it waste the investment in methane capture from POME pond?
No, actually, this technology will complement that methane capture system. Methane capture system will be at the anaerobic stage. They capture the methane, reduce the BOD, but the BOD reduce still not so-called sufficient enough polish to be discharged out or recycled back. So that's where EO comes in. It will take the discharge from that methane facility, polish it, and then we can recycle back. So it complement each other.
Okay, all right. So you sort of like let the biogas handle the methane emission and you to recycle water. So okay,
and then we can use
the
electricity for EO as well.
Okay, I think the commitment to achieve net zero emission, reducing both the water and carbon footprint is commendable and very forward-thinking initiative. So you're not only contributing to a more sustainable future, but setting up a very good example to other industries to follow, right? If this technology can be deployed, I think it solves like half of our problem. So I guess with that, we come to the end of the questions. If you have any other queries, you can reach out to Nick Farid on other platforms. I'm sure LinkedIn, you're available. So thanks once again, Mr. Nick Farid, for the great sharing. And to the participants, just a small announcement. The upcoming event is Palm International Nutra Cosmeceutical Conference, PINC 2023, hosted by MPOC. The theme of PINC 2023 is unlocking the potential of palm bioactive in Nutra Cosmeceutical. It will be held at Lee Meridian, Putrajaya on 22nd August. Feel free to join the biannual conference hosted by MPOC. We do have series of webinar on palm oil processing underway in the coming weeks. So to Mr. Nick Farid, thank you so much for your time and knowledge shared on the technical experience. So maybe some concluding words from you before we end the session.
I think when we look at the palm oil mill, we're always looking at the image of it. So it's time for us to move from what we are now towards more, we can say food processing factory. So not only the mill itself need to be of some standard, the way we handle our byproducts also need to jump to the beyond standard. That's what we are doing now. We are not looking for our main product only. We need to tackle our byproduct, so that we can close the loop, and then we can achieve I would say the true circular economy. And from there we can move forward as the whole industry moving forward.
Okay, that's great. I think I totally agree with you on that. How do we convert all our waste to wealth, at the same time meeting all our compliances to target, making palm oil processing more progressive and sustainable in the coming terms. So thank you so much again for your time. So to all our audience, thank you for listening and see you all in the next webinar. Have a nice day ahead. Thank you.
Thanks, everyone.